Okay, we still have one more element of complexity that we need to add to our model before we are ready to generate simulations of jumping. We added this passive joint moment element here. We still need to add this foot ground contact element here. And lastly, we're still going to need to revise the initial state of our model, but that's not really an element of complexity. We just need to revisit how we're defining its initial kinematics and initial muscle states and things like that. So one more element of complexity to add here, and that's this foot ground contact element. And our consequences of not having it right now are that when I turn gravity back on here in my model and return us to planet Earth, that I just fall right through the ground. And that may seem kind of strange because if we revisit our PyDI code, where we had our model defined here, we had these ground contact or ground reaction forces defined here. Where at point P4 here, which was my foot point, my distal end of my shank segment, I had this horizontal force defined and I had this vertical force defined. So why does it seem that when I'm running my simulation, there's no forces there at that point? My foot's just passing straight through the ground like there's no force there. Well, if I revisit my model's functions here, I'm telling it that there's no forces here. I have these forces fx1 and fy1 defined at that point, and if I inspect my forcing vector here, those terms fx1 and fy1 do indeed appear in those expressions, but because they're being always set to 0 here, they're not affecting the model's motion at all. Sometimes I want this vertical force and this horizontal force to be 0, like when I'm airborne here, right? But as soon as the height of that contact point, that distal end of the shank, becomes non-zero, as soon as it contacts the ground and starts to penetrate into the ground, then I want those contact forces to be non-zero. So we're going to replace our definition here of our applied force with an if statement that says if height of contact point is greater than 0, then go ahead and set my vertical force equal to 0. And we'll revisit the horizontal force later. We're just going to define the vertical force for now. Otherwise, if my height of that contact point is on the ground or beneath the ground, then I want that force to be something else, some function of something. Okay. So I need to define a model here of foot-ground contact. And how can I do that? You'll see some simulations that have the contact point here actually jointed to the ground. And so that would look something like where when I'm airborne, I have these equations here, like I already defined, but then I would detect here when the model is beneath the ground, and then my if statement here would switch to a whole other set of equations of motion here that have that contact point jointed to the ground. That's one method of simulating intermittent contact with the ground. I would say it's not a great method of simulating intermittent contact with the ground. In particular, it doesn't allow for any deformation of the contact points or for any viscous elements of the contact points. And so it's a way of simulating contact, and one that you'll see in the literature in simulating foot-ground contact, but I would say not a great way of simulating intermittent contact with the ground like we see in locomotion and in jumping. So we're going to simulate contact with the ground in a different way. We are not going to joint our contact point to the ground, and we are instead going to define contact here as a spring-like contact point or a viscoelastic contact point, meaning when we are on or beneath the ground, our vertical contact point will be a function of the height of that point, or in other words, the amount of penetration into the ground, and the velocity of that contact point, or the rate at which it's penetrating the ground. So visually here, while we're airborne, if you think of my mouse cursor as being the contact point, while it's airborne, the vertical force there will be 0. As soon as it contacts the ground, the more it penetrates into the ground, and the faster it's penetrating into the ground, the greater the contact force here I want to develop to arrest that motion and stop it from penetrating any further into the ground. The physical motivation here is, if I pull up my video for you guys, photo booth. Okay, if you look at my heel pad on my foot there, and if I push on it with my finger, this is a viscous structure and an elastic structure. Elastic in the sense that if I push on it a little bit, it deforms a little bit. If I push on it hard, it deforms more. Right? So that's the elastic nature of that of my heel pad there. The harder I push on it, the more it deforms. Okay? Now, the force that it resists me with is dependent not just on how much I'm deforming it, but also the rate at which I'm deforming it. It's kind of hard to tell on a tissue this small with motion that's that subtle, but the force that it resists me pushing on it with is a function of not just how much it's being deformed, but the rate at which it's being deformed. Okay? So it's both an elastic structure, depending on the amount of deformation, and a viscous structure, depending on the rate of deformation. It's kind of conceptually similar to what we just defined in the previous video for those passive joint moments, where we had viscoelastic joint moments, where based on the position of the joint and the rate of change of position of the joint, or the joint velocity, we defined a passive moment at that joint. Similarly, for our ground contact, we're going to define viscoelastic ground contact, where the vertical contact force is going to be a function of the amount of deformation into the ground and the rate or velocity of deformation into the ground. So let's label our forces here a little bit more descriptively. There's going to be our ground contact forces. And you can see before we proceed any further here, we need an expression for the height of that contact point above the ground. And fortunately, we already have that because we've been generating animations of this model. We already have P4Y, which was the expression for the height of point 4, that distal contact point on the shank, where we have our contact force defined. So we have that term already, and we can replace height of contact point here with P4Y. Okay. So how can I measure deformation here of the foot, or of the contact point? Well, we're going to do this with a simple linear spring, where I have some spring stiffness, kgc, for stiffness of ground contact, times the amount of deformation beneath the ground, P4Y here. The unspoken assumption is that the unloaded length of my spring is 0, or that when I'm in contact with the ground, when my height of my contact element is 0, then my spring length is 0, and I'm not yet generating any vertical force. As I penetrate deeper into the ground or get further away from 0, or get a more negative height here of that contact element, I take that times my negative stiffness and get a larger and larger vertical force, and the positive vertical force resisting further deformation. Okay. So probably the simplest possible model here of vertical contact with the ground. Okay. These things tend to generally be nonlinear, so we are going to square the height of the contact element there, or square the amount of deformation, so that we get a non-linearly increasing contact force with greater and greater penetration into the ground. Because squaring the deformation is going to force it to be positive, now I no longer want this negative sign out front there. I want to get a negative deformation, square it to make it positive, and multiply it by a positive stiffness there to get a positive vertically directed contact force there. So before I can actually run this model, I'm going to need a value here for the stiffness of my ground contact element. And so where can I get that value from? What's a good value there? Let's define some new parameters here for ground contact parameters. And where can I get this stiffness from? I uploaded 2 papers for you guys to take a look at here. The first one is this review by Namey, which is an assessment of mathematical models for modeling foot-ground contact interaction. Here they go through a number of different mathematical formulations for modeling foot-ground contact. Some similar to the one that I just defined there, some a little bit simpler, some a little bit more complicated. In general, these are all going to be something that's relating the force in the contact elements to their deformation, x, and their rate of deformation, velocity. And then you'll have some expressions here for their stiffness, that's what A would be, and their damping, that's what B would be. And there'll be some other elements of complexity and nonlinearity here. That's where the 1 plus and the multiplying and the cube and the whatnot come into play. But they're all conceptually similar in that the force in a contact element is a function of the element's deformation relative to the ground, or its position relative to the ground, and its velocity or rate of deformation relative to the ground. Now, where would you get values for those stiffness and damping, and how would you define, say, the form of the function? Like, why would you know to use this one versus this one versus this one? Well, typically you would want to do this by considering human experimental data, and that's where this other paper comes in, Eierts and de Klerk. This was a cool study. This is a pretty heavily cited study. It's used a lot in musculoskeletal modeling, where they had humans in this rig here, such that your shank and your foot was fixed in the rig, and your heel was exposed here. And then they had a pendulum that they had a certain mass, and you can't really see it too well here, but they have these strands here, where the pendulum could then swing from the airborne position here, and would then pick up speed due to gravity, and would slam into the heel here, and deform the heel. And the pendulum was instrumented so that they could measure its position and could also measure the contact force between the pendulum and between the heel here. Okay. So from that, they got data for the force applied to the foot on the vertical axis here, and the deformation of the foot on the horizontal axis. So they got here force deformation loops for those impacts on the heel under various conditions. Here you have loops for just two different shoes by themselves, a soft shoe and a hard shoe. Here you have loops for a human foot wearing those shoes, the soft shoe and the hard shoe. A little bit further on down here, you have data for just certain parts of the shoe being impacted. And down here, you have data for barefoot with just the heel by itself being impacted. Okay. So that is the source of where you would typically turn to for data for selecting a model, like selecting a mathematical function that fits those data well, and for selecting parameter values for things like stiffness and damping, adjusting those parameters so that when you simulate, say, these impact conditions in your model, that you get force deformation loops of your contact elements that look something like this. Okay? I'm not going to go to the trouble of that today just because it takes a while and it's non-trivial to set up, but these are, again, a good source of data you can turn to defining parameters for your contact models. We're going to do it slightly simpler today, where if I consider my foot ground contact, if you guys saw when I was pressing on my heel there, and or more broadly, if you just think about how much does your heel deform if you load it with your full body weight under one leg, well, it might deform by about maybe a centimeter or so. Okay? So if I take my equation here for a vertical ground contact force, and I replace my force with body weight, mass times gravity, and then I replace my deformation with 1 centimeter, 0.01, then I can divide both sides by 0.01 squared, and I get stiffness by itself, indicating that my stiffness here can be my body weight divided by a 1 centimeter deformation squared. Okay, and you could adjust this if you wanted like a stiffer contact element. You could say, well, maybe it only deforms by 1 millimeter under a body weight of loading. Okay, or maybe it takes 2 body weights of loading to deform it by 1 centimeter. Okay, so again, kind of a hand-wavy way of defining stiffness of ground contact, but one that gives us should give us generally reasonable deformations, where the foot is deforming during ground contact by maybe a couple centimeters or so, and it's not going to be deforming by feet or by meters unless there's tremendously large contact forces being generated. Okay, so a fairly simple model here of vertical ground contact. We're still setting horizontal contact force to 0. We'll deal with that in a little bit when we finished here with the vertical part. So let's run our model here with our vertical contact force and see what we get. Okay, and now our foot contacts the ground and bounces off the ground rather than penetrating it. Cool. Now notice here that the rest of the model still ends up beneath the ground. This is because we only have a contact element here at the foot. We don't have any at the knee or at the hip or at the top of the head. If we wanted to prevent any part of the model from going through the ground, we would have to define contact forces also at those other points. We didn't do that here, so that's why when the model gets upside down like that, the rest of it's able to go through the ground. If we wanted to just simulate, general motion, we might want to define forces at those other points. For simulating motions where we don't expect any other part of the body to be in contact with the ground, like for jumping or locomotion, you'll typically just see contact elements defined on the foot where you're expecting that interaction to happen. At parts of the body where you're not expecting that interaction to happen, you typically won't see a contact model there. Even though it lets the model move through the ground in an unrealistic way, it's typically not a key part of the motion that you're going to be simulating. Okay, so we'll stick with just contact here between the feet and the ground for now. Okay, now remember we said here that this contact force is typically a function of not just the height of the contact element, but also the vertical velocity of the contact element. And lacking that velocity element or that damping element is why we bounce off the ground so dramatically like this. Our contact hits the ground and kind of bounces up pretty abruptly. Typically when we land, even the absence of muscle activity, our foot kind of sticks to the ground a little bit, or at least it doesn't bounce appreciably off the ground like that. And the reason it's bouncing is because we are modeling it as a undamped spring and not as a damped spring. So we need to add an element of damping here. We could add damping like this, where it's additive damping, where we take some damping rate times the vertical velocity of this contact point. That's typically not the most realistic model of damping for human foot-ground contact. You'll typically see something that's multiplicative damping that gradually introduces damping. You'll see it modeled like multiplication of 1 plus some damping constant times the element velocity. You'll see it as an exponential function that gets multiplied by a damping rate that kind of gradually introduces damping like this. This is one that I've used in the past with some success for generating force deformation loops that resemble these human force deformation loops. So it's a model that I like for this sort of thing. Exponents are generally something you kind of want to avoid in numerical simulations a lot of the time. They can be numerically not the most friendly equations to work with in the world, but for something like ground contact like this, I think it produces reasonably realistic results a lot of the time, so I like to use it sometimes even though it's not numerically the best thing to use. So we'll stick with it here for this fairly simple model. For a more complicated model, if you ran into some numerical issues, you might consider looking for a different model of ground contact here that didn't have this exponent. You can see here we need an expression for my vertical velocity of my contact element. I called that P4V. And I'm also going to need an expression for P4U for my horizontal velocity of my contact element. That'll come into play here in my horizontal contact force. Where can I get those expressions for? I don't already have them here in my plotting because I don't need velocities for plotting, I just need positions. If we go back to our PyDI code, remember we were having it tell us expressions here for velocity at the end. I had it print an expression for my horizontal velocity of my contact point in the global frame and my vertical velocity of my contact point in the global frame. So if I rerun my PyDI code here, I should be able to get those expressions. It should be the last two it spits out there. Yep, P4U for horizontal velocity of 0.4, P4V for vertical velocity. And remember, PyDI's got a bunch of indications that my states are functions of time here that MATLAB doesn't need. So let's do a find replace there. Get rid of all those. Then I can copy those expressions into my model functions here. And paste them up here with below my position. And now I've got expressions for my horizontal contact velocity and my vertical contact velocity. And here's my vertical contact position. Okay. I need a new parameter value here for my damping coefficient there. So value for BGC. You'll typically see values there that are on the order of 1 or so. So let's just arbitrarily set it to 1 here. In reality, you would want to fiddle with both of these parameters to fit your model here to data like this. Like if you're trying to simulate a barefoot condition or a shod condition in like a soft shoe or in a hard shoe, you'd want to generate simulations of these conditions of your model's foot being impacted by a mass under certain kinematic conditions and see what sort of force deformation loops it got and adjust your stiffness and your damping to get loops that resemble these. For here, I'm just going to kind of demonstrate the effect of damping in terms of what it has on our model. So let's see it again here without any damping. I'll just comment out my damping there. And we should see that the model bounces kind of violently off the ground here. Boing. And then if I introduce some damping there, let's then see what happens. You can see we got a much softer bounce there. And then if I ramp up my damping, let's double it to say 2. And do we get an appreciable difference there? And it's starting to give me some numerical issues. But a little bit softer landing. And let's see if I make it real big. Let's see if I make it 10. Can I get him to actually stick to the ground? Okay, and there we're essentially stuck to the ground. You can see here MATLAB's spitting out some orange text, just giving me a warning that my matrix is singular when I'm solving these equations here in my function. Again, sometimes this exponential function here can give you some problems, especially when this term here becomes very large, or the result of this exponent becomes very large or becomes very close to 0. So generally, you don't want to use huge values here for my damping rate. So let's just put it back to 1 there. Where we've got just a little bit of damping, so we only got a little bit of a bounce off the ground instead of our very abrupt and violent bounce off the ground that we had with no damping. Okay, so there is our model of our vertical ground reaction force. We still need our horizontal ground reaction force, Fx1. And for that, we're going to use a Coulomb friction model, which is going to be my coefficient of friction times my vertical force. So I need a value for a coefficient of friction. And for human feet in contact with normal ground surfaces, that's typically on the order of 1 or so. So we'll set that equal to 1. Problem here is that my vertical force is always positive, but I don't want this horizontal friction force to be always negative. I want it to be negative when this contact point is trying to slide in the positive direction, and I want it to be positive when this contact point is trying to slide in the negative direction. Ideally, I want to simulate here what's called stiction, which is when my contact point is in contact with the ground, it's stuck there in the horizontal plane. It can't move forward, it can't move backwards, it's stuck there until contact ends. Or in other words, it doesn't slide, it doesn't slip, it's just stuck there due to friction until the contact element vertically leaves the ground. That is easy to describe analytically and verbally. It's very hard to achieve numerically in practice, and so you'll often see this horizontal frictional force described in modeling papers with foot-ground contact as a Coulomb friction approximation, where rather than having a true Coulomb friction, which would look like this, where it would be just the the coefficient, the negation of the coefficient of friction times the contact force times the sine on the horizontal, sorry, that should be P for U for horizontal velocity, times the sine of the horizontal velocity. We will typically use something that approximates this sine function here, which is a number of candidates, but one that I've used before with some text or some success is the hyperbolic tangent here, where we take the horizontal velocity and divide it by a constant Vs that I'll explain in a little bit. This is a function that approximates that sine function, where it makes my friction force positive if velocity is negative, if horizontal velocity is negative, and makes my frictional force negative if horizontal velocity is positive. The smaller this Vs constant here, which is the specific speed, the smaller that is, or the closer it is to zero, the more closely this hyperbolic tangent approximates a true Stiction, true Coulomb friction. If I make it literally zero, then I get a divide by zero, and things numerically blow up here. So I'll make it some value that's pretty close to zero, but not exactly zero. And I know from experience that Vs is typically something on the order of 0.1 to 0.05 to get reasonably close approximations without being too close to zero to give you numerical problems. So we'll try a value of 0.5 there. Again, this is one you might play around with you might play around with both of these parameters here to fit this to to human data that you have for, say, horizontal foot-ground reaction forces or some sort of reference on these things. I'm just selecting these parameters kind of arbitrarily here to demonstrate their effect here. Okay, so now I've got a model of vertical ground reaction force and a model of horizontal ground reaction force. It's giving it an orange one here because I still have my original definition as zero there. Let's get rid of that. Okay, and so now we have a vertical force and a horizontal force, and let's run our simulation here and see what we get. Okay, we have a model that is contacting the ground and is not sliding too much relative to the ground. So a vertical ground reaction force and a horizontal ground reaction force as well. Okay, that is it for now. We've added passive joint moments, we've added ground contacts, and now all we need to do is fiddle with our initial state and we will be all ready to go to simulate jumping. So we will tackle that final task next time.